take small volume again, but get a proof in 2 dimensions. A wild speculation about how to solve this in 3 dimensions. So I think there's a small number of people who maybe were not the first lecture. So we'll work with dyadic intervals, and maybe I'll just change the color. So I would denote a dyadic interval, and we will rely very much on the fact that if you split a dyadic interval into 2, so this would be I, you split it into 2, and then the left half and the right half are also dyadic, and we find, forget my draftsmanship, this is the R function associated with interval I, so it takes the value -1 on the left half and +1 on the right half. And now we're especially interested in rectangles, so R1 cross RD would be dyadic. These are dyadic rectangles, so a product of dyadic intervals. And the R function associated to this is the tensor product, Rj of xj, so the product from 1 to 2, from 1 to d, of an R associated with each side length of the rectangle. And now, I want to concentrate for a moment on dimension 2. So in dimension 2, a rectangle, dyadic rectangle would then be split into 2 pieces, 4 pieces, by dividing each side length, and then the R function would take the value +1, +1, -1, -1. And now we use the technology for in this special circumstance in dimension 2 is that if I draw a second rectangle that looks, for instance, like this, I divide it in 2. Let's call this R, this S, and HR times HS will be, choice of sign, the R function associated with the intersection. Okay, so it's a product rule. The product of R's is R. Of course, we need to specify that the R's should be adapted, that you don't have, that the sides of the triangle, the rectangles don't line up, but aside from this restriction, we have a product rule. The product of R is R. Okay, and now, so the small conjecture. I would prefer, this is admittedly slightly confusing to new people, but I would prefer to just restrict attention to the case where we take sums of R's and we keep coefficients to be either -1, 0, or 1. And then we take the sum of the A sub R and H sub R L infinity is bigger than n to the d over 2. Except I can obviously violate such an equality if I set all the coefficients to be 0. So we agree that half the coefficients, or a quarter of the coefficients, let's say a quarter, are non-zero. So we agree that I should restrict volume, which I forgot to mention. It's very important that you restrict the volume of the rectangles. For each n, you sum r's with the volume of the rectangles fixed, and you should, and then the conjecture says you get n to the d over 2, ignoring the constants that depend on the measure. The obvious way to violate this is set all the coefficients to be 0. So we agree that only a quarter are 0. So as we explained last time, if you replace the L infinity norm by the smaller L2 norm, then what you get here is n to the b minus 1 over 2. And so the conjecture is that the L infinity norm is always bigger by at least this factor of the square root of n. The jump you from n to the b minus 1 over 2 to n to the b over 2. So this is for dimension 2, so d equals 2. This is theorem of Michel-Pellegrin from 1990. So now let's get proof for d equals 2. This is the proof that was shown to me by Lloyd Templeton. The set, so dimension 2, just to, again, as I iterated last time, in dimension 2 we have a special circumstance that this is exponent 1 and a given x is contained in about n rectangles. So we need to find a point where all the r's are plus 1. So the proof actually builds uniform measure on a set of such x's. So it equals, and to build uniform measure, we're going to use a Rees product. The Rees product, I need auxiliary function. So we define functions. And so F, so J is going to be the sum over R's, so the volume is this fixed quantity. But we further specify the first side length, R1, to be 2 to the minus J, which in the two-dimensional case means that the second side length is given. Now I take the R function, and now I take the signum of AR, which looks a little odd, because this AR is either minus 1 or 1, but I don't want 0 to appear. So we agree that the signum of 0 is 1. Okay, so this is a nice function, just to draw a very simple picture. So this would be the unit square, and now I take the first side length of the unit square and divide it into intervals of length 2 to the minus j. Then the area is fixed, so the second side lengths are then given to me. Okay, it's not dyadic, that gives the impression. And then on each one of those squares, I either take the har sort of up or the har reversed, depending on the signum of A sub r. It's nice, simple, useful exercise to verify that the f sub r's, the f sub j defined here, are independent functions. So they're independent random variables taking values plus 1 and minus 1. Okay, so proof, so we construct psi in L1 such that psi inner product with the sum we want is bigger than n. And psi is the product from 1 to n of 1 plus fj. So it's, remember that these take the values either plus 1 or minus 1. So we're taking the product of a sequence of 2's and 0's. So obviously it's a positive function. The fj's are independent random variables. So product of expectation of product is product of the expectations. So the expectation of psi is 1. So it's a positive function with whose integral is 1. So it's an L1. So we just need to understand what happens with the inner product. So that's also straightforward. So you write psi as 1 plus psi 1. Well, psi 1 is the terms that are linear in the fj's. Plus psi 2, which would be the terms linear, the second order in the fj's, and so on. So 1 is obviously orthogonal. Function we're testing. Psi 1 by construction gives you, remember the psi 1 is the fj's, and the fj's are defined in terms of the signum of the a star h star, so all the sign cancellation drops out. You perform this inner product. And so you get that this is the sum of integral absolute HR, which is basically, well, the integral of absolute h sub r is minus 2, is just the area of the rectangle. And how many times do we pick up the area of the rectangle? Well, basically n times 2 to the n times. By our agreement that only a quarter of all the coefficients are 0. Well, what happens with the higher order terms? Take psi j, which would be all the sums of all products of j-fold products of the f sub r, f sub j. I'm sorry, let me say k phi sub l. So this is a sum of f j1, f jl against this. Well, remember the f sub j's are independent random variables, so when you multiply the independent random variables, you push, you get something that is again a linear combination of R's, but the R functions have smaller area. That's what the product will tell you. So this inner product, all of these inner products are identically 0. And so that's the complete proof. So let me just write down psi was product from 1 to n, 1 plus fj. And since the fj's are only taking the values plus or minus 1, this is obviously equal to 2 to the n times the indicator of a set. The set E is the set where each fj is plus 1. And psi has integral 1, as we argue, so we know that this set has measured 2 to the negative n. So measure B is 2 to the negative n. Notice it's useful to keep in mind that this has a nice interpretation in terms of Gaussian distributions, because we were looking for, we found values where we were above the standard deviation estimate, or the average case estimate, by a factor of square root of n. And so if things are really governed by the Gaussian distribution, which they are in 2 dimensions, then I should get an e to the negative square root of n squared, which is exactly what I'm finding. So this is actually an extraordinarily precise estimate. So I gave a very crude heuristic for why the 3-dimensional case was much harder. So let me give 2 additional reasons why the 3-dimensional case is much harder. The first is as this proof already shows you, the product rule for HARs entered in a completely decisive way. Sort of simplifying the analysis a great deal. So the product rule fails and D equals 3. This is I mean, if you just think about it for a second, it's clear. You have two dyadic boxes in 3 dimensions with the same volume, they just happen to agree in one coordinate. So just a simple picture is look like this. So if you now think about what these Haar functions would have to look like in 3 dimensions, well, what is the product? So call this R and this S, and consider the product HR times HS. Well, in this direction, no cancellation. It's completely gone. But, and this is a fact that we will exploit explicitly, in the other 2 directions, you have cancellation. So here, we'll have the plus, plus, minus, minus. And so I'll show you how to exploit that in a concrete way to gain non-trivial results in 3 dimensions and higher. Okay, so the product rule fails, and so this actually complicates life quite a bit.
Aren't you tempted to draw a 3rd box? Triple intersections.
Triple intersections. Well, I mean, you already get stuck with pairwise intersections, so we have, in 3 dimensions, we have precise information about the coincidences, and I'll give you And we can exploit it in specific ways. For the proofs of the theorems, we do need an analysis of longer products, yes. But first you have to understand theorems. So now let me give. Oops. I've now done something bad. So I'd like to illustrate a proof strategy, which I think would be to, if you solve this conjecture, I think you would argue along these lines, as we currently understand these arguments are just too ambitious to fully implement. So dimension 3. And let's set H to be the sum of R's equals 2 to the negative n, A sub R, H sub R. And we continue with our assumption that only a quarter of the coefficients are 0 and otherwise are plus or minus 1. And now let's just keep the numerology in mind. So what is the L2 norm? The L2 norm is basically n, because each point is in more or less n squared rectangles, and so we take the square root of that to get the L2 norm, and then conjecture is that H infinity is bigger than n to the 3 halves, and so there's a big question mark is there. Well, to try and analyze this thing, you sort of need auxiliary functions in some sense. And so this time, the auxiliary functions have sort of a formally similar definition. Sum over rectangles of a fixed volume as before. And now let's fix the first side length, just like before. 2 to the negative j, A sub r, H sub r. So if I'm in 3 dimensions, and I fix the first side length, then it's essentially a 2-dimensional sum. And the behavior of the sum should be governed by the 2-dimensional class. So now the H sub j's are just like in the 2-dimensional case, so very well behaved sums. And so H sub j generically, and this can be made rather precise, is of order square root n. In fact, there's some sort of CLT in play. There are 2 dimensions, so if you calculate L2 norm, since you fix the first side length, each point is in about n rectangles, so the behavior is like square root n. But in fact, there's a very precise CLT, because you have some sort of independent structure, which I've already alluded to in the 2-dimensional argument. So you want to, so the goal is to show, and this is where the hopelessly ambitious strategy is to show the intersection from 1 to n of Hj is bigger than some constant square root of n is not empty. So if one can show that, then at that point, test the L infinity norm at a point in such intersection, test the L infinity norm, and you get the end of the 3 halves. Moreover, how big should this set be in measure? Each set has probability bounded below by a constant, call it a half, by the central limit theorem that I'm alluding to. So for small enough c, each set will have probability at least a half. If the sets were literally statistically independent, which is the case in dimension 2, right? The probability of this event would be 2 to the negative n, which exactly matches the sort of Gaussian behavior which should come in the situation. So the hopelessly ambitious part is to show that these sets are, in some sense, conditionally independent. And in the last hour of these lectures, I plan to implement this strategy, but not prove a conjecture, not to actually prove anything useful, but at least illustrate an argument which I believe is of the correct nature to solve the conjecture. And it's also a lot simpler than our actual proofs, which get very hard. So now I've tried to give 3 explanations why in 3 dimensions is just a lot harder. Hopefully one of them appeals to you. I want to say, in the time that remains for this lecture, I want to say a few more words about why one would be interested in such an inequality, besides the fact that we all like to bang our heads against pretty thick walls from time to time. The most classical aspect which these inequalities are related to the theory of the discrepancy function, sometimes known as the theory of irregularity distribution. So to recall the definition, P is called the distribution of points in the unit square or cube. These are sort of the relevant choices of dimension for these lectures. By convention, the cardinality of the set points is n. And then the discrepancy function, which is usually just denoted, its dependence is usually just denoted on the cardinality of the collection of points, not the collection of points itself. At point x is the difference between a counting part minus a linear part. And I've written it this way because I'm running out of room on the slide. So the counting part you take your selection of points P, you intersect a box anchored at the origin and at point X inside the unit Q, and then you count. So we just pick the cardinality. And the linear part is the number of points that you'd expect to get if things were truly behaving as independent. So this is just the volume of the box times the number of points. So picture, which we've already seen in one lecture, but we just so you take the square, say, throw some points down in some way, and then if you have point x, so in this case, you draw point x, and now you count the number of points that are inside the rectangle, so that's 4 in this case. That's the counting function. And I think so the basic estimate here is the theorem of Roth. This is Klaus Roth, who received Fields Medal for his work in algebraic number theory. It's also the Roth theorem, three-dimensional progressions. And he's 80-something years old. The basic estimate here is dn L2 is bigger than log n d minus 1 over 2. d minus 1 over 2, that's the exponent in the average case estimate that I've been talking about. So the Roth theorem, as we'll see in the proof, is a rather precise analog of this simple average case estimate in the context of the small volume equality. So it's a remarkable result in proving results of different people that began with Van Ehrenfest from the 1930s. This is 1954 result. Regardless how clever one is at selecting the sequence, the sets of points P inside the unit cube in dimension D, the discrepancy function is always at least as big as this bound. And this is the sharp estimate. Okay, so proof. The key point is to look at the R coefficients dn HR with the volume of R being basically 1 over twice the number of points. So the proof will actually make projection onto such R functions, estimate the L2 norm there, and provide the bound, and then there are extreme examples where this method of proof is basically sharp, ignoring constants that depend on the dimension, which still elude us, even in the average case estimate. Why should this possibly work? Well, this part should sound familiar. There's capital N points. So if I fix the side lengths of the rectangles, there's twice as many rectangles as points. So half the points don't meet the point set, and this will be the critical factor that will exploit. So we're sort of we deliberately place ourselves in a situation where half the rectangles that we're dealing with do not intersect the point set. So now we have basic, so now the lemma is, suppose R intersects the selection of points that the discrepancy function is built out of, P is empty. Then the discrepancy function HR, we can, evaluate exactly minus 1 over 4 to the dimension n volume of rectangle squared. And I believe this is the correct formula, keeping in mind that the R function is still bounded, makes the values plus or minus 1, not normalized at all. Taking the limit for granted, the proof of appearancy is straightforward. So remember, I stressed that the discrepancy function was a counting piece minus a linear piece. We'll draw a picture to illustrate that under the assumption that the rectangle does not contain any of the points, that the R function is orthogonal to the counting piece. The inner product is determined. Notice the minus sign. The inner product is determined by the linear piece, which is totally elementary. So the counting piece is, I'm going to express it in slightly different language, but it's the same function. So sum over the points that you've selected, indicator of the rectangle that's anchored at the point P and the upper corner of the rectangle 1. Evaluated at x. So to check that the Haar function is orthogonal to this function, it's enough to check that the Haar function is orthogonal to each one of these. So, and in fact it's enough to check the case dimension 1, but let me draw dimension 2. So here's P. And now, oh boy, let me choose red, or this purple thing. So now let me, if the Haar function is down here, it's obvious that the inner product is 0. So there's essentially only one interesting case where the Haar function looks like, say, this. But then one integrates in this coordinate to see that you get integral 0. And then the only other case to worry about is like this, but that's just interchanging the roles of the coordinates. So that verifies that this equals 0. So now if I go to a new page, switch back to this. So now the inner product dn hr, under our assumption that the rectangle doesn't contain any point, is equal to minus n times xj, hr of x, and it's straightforward exercise to verify this is minus n 4 to the d r squared. Okay, so the proof of Roth is you just use Bessel. Let me take norm squared of dn.
is bigger than the sum over R is... Okay, so I write R equals 1 over 2 to the n, but clearly this is not important. I just need that the rectangle be bounded above by 1 over 2n and then below by 1 over 4n, say. So of dn hr squared, except this is not right for the typical reason that these are not normalized in L2, so I have to divide by R to keep the L2 normalization. Now this is just Bessel inequality. And now I just compute, ignoring constants, 1 over R. 1 over R is basically n.
How I need to do one more property here. R intersect P is empty. Well, how many such rectangles are there? Again, because of the way you choose the volume of the rectangles, basically half the rectangles satisfy this condition. So I need to account for the number of rectangles, which is 2 to the n times n to the d minus 1. Well, n to the d minus 1 is the little n to the d minus 1 is the term I want to keep. That will prove Ross theorem. And now what is the inner product squared? The inner product squared is n 2 to the negative n squared. So the inner product was this capital N times the volume of the rectangle squared. The volume of the rectangle is 2 to the negative n, so I've got minus 2n. This times this is basically 1 over n. And 1 over n squared cancels this and this. And so I have the n to the d minus 1, and that's the n. So Ross theorem is seen from this perspective as a precise analog of this average case bound. And so what is then the analog of Talleyrand's theorem, whose proof we've gone through? The analog of Talleyrand's theorem is the theorem of Schmidt. 1972. Dimension 2. dn and L infinity. 0 minus squared is bigger than log n. So again, the square root log n is Roth theorem, the average case bound. Schmidt says gain the square root.
And in fact, Halaz has found a proof of this estimate. Schmidt's original proof was inductive on capital N. But then Halaz found a proof of this inequality, which is a very close cousin to the argument I've just given you, of the Talleyrand theorem. So these things are in very close analogy in dimension 2. Okay, and so then in light of that, the conjecture the way that I believe the conjecture should be formulated is that in dimension bigger than or equal to 3, dn and L infinity is bigger than log n to the d over 2. But the best known upper bounds, so the best known constructions of sets whose discrepancy is small and L infinity have the d minus 1 here. So as in high dimension, there's a big gap. And so then it's the theorem that I've alluded to already, and Dima Billick has already mentioned, of Billick, myself, and Vagyar Shakyan. I'm not spelling that. I can blame my misspellings on this poor writing service, is that for all dimension d bigger than or equal to 3, there exists an eta of d such that dn L infinity is bigger than log n to the d minus 1 over 2, which is the Roth exponent, plus eta of d. And the prior result in this direction was dimension 3, with this term replaced by something that was log-log. It was a beautiful, intricate argument of Joseph Beck that we rely on some essential features of that argument. So this eta of d decreases like 1 over dimension squared. And this is the first improvement in the Roth exponent in dimension 3 and higher. And the proof of Talleyrand theorem is beautiful and concise because you have very precise information about the Haar spectra of the function whose L infinity norm you're testing. The information you have about the Haar spectra of the discrepancy function, is a lot weaker, which imposes much higher restrictions on how you build the test function. So the proof of this is hard, and I certainly don't have any heuristics at all for simplifying that argument. And indeed, that's sort of a major question. 1 minute, then I'm finished. Thank you.